So let's talk about systems of linear equations. Okay, we're going to start with what is a linear equation first of all, and I've got two examples here of linear equations. This first one is a linear equation in two variables, x and y, and this is a linear equation in three variables, x, y, and z. We'll see linear equations in more than three variables, and a lot of times in those cases, instead of using x, y, z, and other letters, we'll simply use maybe the variable x with subscripts to indicate the different variables. So maybe x subscript 1, x subscript 2, x subscript 3. Why are these called linear equations? Well, first of all, let's look here. If you were to look at the graph of this equation, the graph of this relation, the set of all ordered pairs x comma y that satisfy this equation, and you plotted those x comma y pairs, you would see the graph of a line, right? This graphs as a line. In fact, you can solve this equation for y, and you would get y is, in slope-intercept form, y equals mx plus b, and you can do that. And so that's why this is called a linear equation, because this is going to be the graph of a line. Of course, here, when you have three variables, then, especially if you've had some calculus 3, you've probably looked at this. This is actually the equation of a plane, not a line, but a plane in three-dimensional space. But it's still a linear equation. Algebraically, you can tell it's linear because you have the variables given in the equation only to the first power, and so they can't be raised to any other power, squared or cubed. Can't divide by any of the variables. You can't multiply variables together, and there's no other functions like sine or cosine or the exponential log functions in any of these equations with arguments involving the variables. And so these are linear equations, and this is what this course really focuses on, linear equations. So let's just look at this first one here. Can you think of some solutions to this linear equation? When I say a solution, I mean values of both x, the variables x and y, that make this equation true. Okay, and I think you can see one maybe that jumps right to mind, and that is if you let x be equal to 1 and y be equal to 1, you'll have 2 times 1 is 2, 3 times 1 is 3, 2 plus 3 is 5. That certainly satisfies that. Now, a lot of times when we're writing solutions that involve solutions to equations with more than two variables, we like to list them in an ordered manner. So if I want the x variable first, I would say one solution would be x is 1, comma, y is 1, right? So it's sort of like an ordered pair we're listing. This is x is 1, y is 1. But there's other solutions. For instance, I could let x be equal to, say, 2, and the minute I do that, 2 times 2 is 4, I'll need this product to be equal to 1 to get 5, and so 3 times what is going to be 1? Well, that answer is 1/3. Okay. I can also do something like this. What if x is negative 1/2? Then 2 times negative 1/2 is negative 1, and I now need this to be equal to 6, so that the sum is 5. Well, in that case, 3 times y being equal to 6, y is 2. Okay, and this process can go on. You can probably come up with some others on your own if you're looking at this. In general, we can find how many solutions. Well, there's infinitely many. We've already said that this relationship, if we were to graph it, is a line in the plane, and so there's infinitely many points on that line. In fact, if I go ahead and solve this equation for y by first subtracting 2x and then dividing by 3, so I'll have 5/3 minus 2/3 x if I divide by 3. There's the equation in a form that we can quickly get solutions. In other words, I can let x be any number, and I'll get the corresponding value of y. For instance, if x is 1, like we had here, if x is 1, I get 5/3 minus 2/3. That's 3/3, which is 1. That's what the y value is. If x is equal to 2, I get 5/3 minus 2 times 2, 4/3. 5/3 minus 4/3 is 1/3. That gives me that value, and so on, right? So I can generate that list. So a lot of times this is the way we think about that relationship in an easier manner. Same thing here. We'll look at the solutions to this equation that was up here. 3 variables. Okay, it's a little bit trickier here, but I think there's one that jumps right out at you since these 3 combinations, so-called linear combination of these 3 variables equals 0. Then one solution is when x is 0, y is 0, and z is 0. And notice we have what we call ordered triple here. Ordered triple. First is the x, then the y, and then the z. That's one possibility. And if you play around with it, here's another one. If x is -1, y is 1, and z is 1, that would work because we get -1. 6 times 1 is 1, so -1 minus 6 is -7, and then 7 times 1 is +7. So that would add up to equal to 0. And again, you can probably come up with some others if you think about it. But again, an easy way to do that is to solve for one of the variables. In this case, the variable easy to solve for would be x, because all I have to do is add 6y and subtract 7z, and so I get x indeed is 6y plus 7z. And now you can see how I can generate solutions. You choose y and z to be anything you want. Oops, I'm sorry, this should be minus 7z. I think I said that, but I didn't write that, excuse me. Minus 7z, all right? And so now we can generate all these solutions. Obviously, when y and z are 0, x is 0. And when y and z are 1, I get 6 minus 7 is -1, which is the value for x. And so on. So I can generate as many of the infinitely many solutions to this equation as I can. In general, a linear equation can have any number of variables, and so I'm showing you arbitrary n variables. How do we do that? Well, the variables here are x with subscript 1, x with subscript 2. The 3 dots are what we call ellipses, meaning the pattern continues, so it'll be x sub 3, x sub 4, all the way to x sub n. So there's n variables there. Now these a sub 1, a sub 2, and so on, those are the coefficients. So like here, the coefficient of x sub 1 is 1. If y is x sub 2, the coefficient a sub 2 would be -6. And then a sub 3 would be +7. So those are the coefficients. Of course, b is this constant term over here. And then the solution is what we call, well, this was an ordered pair. This was an ordered triple. If we have 4, it's called an ordered 4-tuple. If there's 5, it's an ordered 5-tuple. If there's n variables, ordered n-tuple. Okay, that's a fun word, n-tuple. Okay, so that's the solution. And there are problems where we have more than 3 variable quantities of interest. There are lots of problems where you have many variables that are related in a linear fashion, and you want to be able to talk about the problem. Now, if the b, remember that's this so-called constant term, right? B was equal to 5 here, but it was 0 here. If b is equal to 0, we call the linear equation homogeneous. Homogeneous. This is not homogeneous, so it's homogeneous. And in linear algebra, this simply means a linear equation where the constant is 0. And because of that, one thing we realize right away for any homogeneous equation, that we will always have one solution for sure, which is where all the variables are equal to 0. We sometimes call this the trivial solution. Now, when we are describing solutions to a linear equation, like we've done above, we will normally express one variable in terms of the other variables and then assign arbitrary values. Okay, and these arbitrary values are what we call parameters. And the letters we use typically for parameters are listed here, R, S, T, U, V, and W. We can use other things. Typically our variables are X, Y, or Z, or X1, X2, and so on, but we like to use these letters for the parameters. Okay, the process of writing the solution in this manner results in parametric equations, or I call this process parameterization. So if you ever hear me say parameterize something or write the solution in a parameterized way, that's what we're talking about. And that only happens when we have infinitely many solutions. So if we go back to these, remember 2x plus 3y equals 5. Remember we solved above and we said y was equal to 5/3 minus 2/3 x. So one easy way to parameterize the solution is to solve for one of the variables like we did here. And then since I solve for y in terms of x, I'm going to let x be my parameter. Let x be, say, I'll pick t. Okay, t is my parameter, so x is t. And then, what's y? Simply replace x with t, and I get this. Okay. Or if I want to write it then out, how would I write this solution out? Here's the parameterized way. Remember, it's ordered pair, x comma y. What is x? X is the t. What is y? 5/3 minus 2/3 t. Okay. And this is the way we like to express solutions when we have infinitely many solutions in a parameterized way. And this is helpful. A lot of you are going to be maybe do some programming. Some of you may be computer science majors. And it's very common to be able to talk about a parameter or an index, right? You might have a for loop, for t equal 1 to something, do this, or for different values of the parameter, evaluate this, and so on. And so it's very conducive to being able to write the programs that will support, and we're going to look at some algorithms in this course that you would want to, especially if you're a computer science person, think about how would you program that? How would that be programmed? Okay, let's look at this other case. Of course, this is 3 variables. How would a parameterization look like that? In this case, remember we solved for x above, and we got x was equal to 6y minus 7z. And again, here x is in terms of 2 variables, so these 2 variables are kind of free to be chosen, if you will, and those will be the parameters. So I'm going to let y be the parameter, choose r, and I'm going to let z be t. Okay, I like r and t. Those are my favorite 2 parameters. And then what's my solution going to be? It's an ordered triple, x, y, z. What's x? Well, x is now what? 6y, but y is r. So it's 6r minus 7z, which is t. That's x. Y is what? R. And z is t. And this is the way we would write the solution to that linear equation. And you can see, again, it's very conducive. You simply choose r or t to be any real numbers, and you'll generate a solution, right? You'll generate a solution. Okay, so we've talked about a linear equation. What this section is about, though, is a system of linear equations. So when we say a system of linear equations, we're looking at more than one equation. Okay, we have more than one equation. So let's look at some examples of that. So here's a little example here. This is 2 equations, and there's 2 unknowns in each equation. We'll stick with x and y right now. We can do the x1, x2, and so on, and we will start doing that more here in a little bit. So how would I solve this solution? What do I mean by how would I solve this system, rather? What's the solution to the system? Well, here we're talking about the values of x and y that satisfy both equations, okay, simultaneously at the same time. So we know that each equation represents basically what? A line. So there's infinitely many solutions for each. But the question is, what, if any, are the values of x and y that satisfy both? Okay. So first, algebraically, we're going to look at this, and then we'll look at it geometrically. You should be familiar with 2 methods of solving systems of linear equations. One is substitution, and the other is addition or elimination method. In both of them, basically what you're trying to do is eliminate one of the 2 variables and get an equation that has just one variable. And so substitution, we'll do that one first, is pretty easy to do. You choose to solve one of the equations for one of the variables. And I'm just going to look here and say I'm going to solve the second equation here for y. Right? And all I have to do is what? Add y and subtract 7. And I'll get y is equal to negative 4x minus 7. So you see what I did in a couple steps there. I added y and I subtracted 7, and then I kind of swapped sides. So I'm going to get negative 4x minus 7 is what y is. So there I've solved for y. Okay. Solve for y in second equation. And then I'm going to plug this in. I'm going to plug in this value into the first equation. Okay, and so this is 2x plus 3 y, but I'm going to replace that y, which is negative 4x minus 7, into that equation equals negative 1. So there's that first equation. I replaced y with the corresponding expression for x. Now I have one equation in the variable x. I can solve for x, distribute the 3, I get negative 12x minus 21 equals negative 1. 2x minus 12 is negative 10x. Add 21 to negative 1 gives me positive 20, and so I get x is negative 2. Okay? So the value of x being negative 2, what's the value of y? Well, I come back up here, and in a step that we sometimes call back substitution. So I'm going to go back to this original equation where I solved for y, and now replace x with what? Negative 2. So I get y is negative 4 times negative 2 minus 7. That's positive 8 minus 7. Y is 1. And so my solution is x is negative 2, y is 1. That's algebraically one way to solve. Algebraically one way to solve. Another way to solve is by elimination, or addition sometimes called. I'll just show you real quick with this one how we can do that. If I simply, with these equations lined up, you'll notice I've got all the x terms over the y terms lined up and then the constant terms. When we're in that format, it makes it easy to see this. Notice here I can eliminate the y variable by simply multiplying the second equation by 3 and then adding the equations, right? So if this equation says these two quantities are equal, right? If a equals b, and then here I got c equals d. Well, if a equals b and c equals d, then when I add a plus c, that should be equal b plus d, right? So I can add equations in that manner. And that's what I'm going to do. So I'm going to take the first equation, 2x plus 3y equals negative 1, and I'm going to do times 3, second equation, times 3 will give me what? 3 times negative 4 is negative 12x. 3 times negative y is negative 3y. And 3 times 7 is 21. And now I add. All right, I'm going to add these together. And so when I add 2x minus 12x, that gives me negative 10x. 3y minus 3y is 0. Negative 1 plus 21 is 20. And that sounds familiar from over here, right? And so what do you get? You get x is equal to, again, negative 2. Same thing. And then what? Well, I haven't solved for y. I mean, I could have in either one. But I can just plug this negative 2 in for x for either equation. It doesn't matter which one. I can plug it into either one. Okay, so I can back sub into either equation. Okay, and when you do that, you'll get that same solution. I'll let you do that. So you should be somewhat familiar, I hope, with these two methods. These are good algebraic methods. It's a little bit harder when you have more than two variables. Then you have to sort of do this a few times to eliminate a common variable, and then sort of work your way down. That's ultimately going to be our goal in the course. Let's look at a couple more examples real quick. Solve these equations, and I'm going to do this by the addition elimination method, because I notice, hey, I've got 2x here, 4x. If I multiply this equation up top by a negative 2, I'm going to get negative 4x positive, right, negative 2 times negative 3, positive 6y equals 1 times negative 2 is negative 2. And then I just rewrite this equation down here. And then I'm going to add, right? Negative 4x plus 4x is 0. 6y minus 6y is also 0. right? Negative 2 plus 3 is positive 1. Well, what happened here? I mean, here we had a variable and we were able to solve for it. It's like everything disappeared over here. What does that mean? Did we do something wrong? Does this not work for this particular system of equations? No, nothing's gone wrong, but what we're left with is this equation, 0 equals 1. And what would you say about this equation? Well, I hope you would say that's crazy, right? That's nuts. That is false. It is a false statement, or what we call a contradiction, right? 0 can never equal 1. What this indicates, right? So this is a contradiction, and therefore that tells me that there is no solution to this system. In other words, there is no value of x and y that will satisfy both equations simultaneously. There's no value of x and y. There's lots of values of x and y that will satisfy any one of the two equations, but none that are in common. None are in common. Okay, so that's an interesting situation. Let's do one more. This one we'll do with substitution, because I can solve this first equation for y pretty easy, can't I? Just subtract 3x. And then I'm going to sub in 2 times y, which is now 2 minus 3x, equals 4 minus 6x. And when I distribute 2, I get 4 minus 6x. And immediately I think you begin to see something interesting here, since both sides are identical for all values of x. In fact, if I subtract 4 and add 6x to both sides, I get 0 equals 0. Now, it's kind of like what we had up here, where I sort of eliminated the variable, but this time, instead of a contradiction, I get an identity, a true statement. This is an identity. It's always true. In other words, it doesn't matter what value of x I plug in here, this will always be the case. Okay. So what does that mean? It means we have a solution. Does that mean we have what? Infinitely many solutions is what that means. Okay. So what is the solution? Is it all what? What are we looking for? Not just values of x, but values of y. Is it every x and y pair that works? Every x and y pair? No. It's just the ones that satisfy this particular equation here. And in fact, you would see if you solve for y here by dividing by 2, what would you get? 4 divided by 2 is 2, 6 divided by 2 is 3. I get that same equation. These are identical equations, right, essentially. And so we have the same line. And so there are infinitely many solutions. And how do we write out infinitely many solutions? Well, we are going to parameterize. What we talked about just a minute ago, parameterize. And so here, right, I have the idea behind the way to parameterize. Since I've solved for y here, the values of y and x must satisfy this equation. I'm going to let x be the parameter, let x be t, and so y is going to be what? 2 minus 3t. And so my solution will be x is t, comma, y is 2 minus 3t. So these last three examples illustrate basically the three situations that we end up having when we have a solution to a system of linear equations. Namely, we are going to have either one solution, one unique solution, right? One solution to satisfy both equations, or no solution, or infinitely many solutions. Not every ordered pair, but only these, right, of this form, in this parameterized form. Now, some of you are familiar with the fact that we can look and think about these same problems geometrically, and that's what I've done here. These are the same three systems we just solved. And the first one, you remember, the solution was what? Negative 2 comma 1. Look where these two lines intersect, right? If I solve for y for each of these, each line here comes from one of the equations. So we have two lines that intersect at a point. That's going to give me one solution. Okay. The second case, where we had no solution, if we look at these lines, then we're going to get two lines that are parallel. And my dog is barking in the background. I apologize for that. we get two lines that are parallel. They never intersect, and therefore there's no solution. And in the last case, if you remember, if we solve for y for both of these, we get the same line. These are coinciding lines. Both lines are right on top of each other. And we have infinitely many solutions, all the points that are on this particular line. Okay. So systems of equations with at least one solution are called consistent systems. And so the two consistent cases are where we have one solution or where we have infinitely many. Okay. A system of equations with no solution is called an inconsistent system. So this system up here is inconsistent. Now we're not going to prove this yet. We will later. But in fact, for any system of linear equations, no matter how many variables there are, these are the only three possibilities for the solutions. One solution, no solution, or infinitely many. We haven't proved this for the cases where we have more than two variables, but we do have, essentially a good feeling about it, at least for the two variable case. Okay, I'm going to stop here, and then we will talk more about how do we solve for the solution to a system of linear equations when we have more than two equations and two unknowns. And that's really what we want to get at. How would you do it? You don't want to do it this way by hand if we have, say, 100 equations and 100 unknowns, right? How do you do that, right? And so obviously, technology can help us with that, but we need to understand the algorithm and the routine, and that's what we're going to be building toward in this course at the beginning. Okay, so we'll stop here.